Let's take a look at the flood fill question from the Grind 75 question list. An image is represented by an m by n integer grid image where image ij represents the pixel value of the image. You are also given three integers, sr, sc, and color. You should perform a flood fill on the image starting from pixel image sr, sc. To perform a flood fill, consider the starting pixel plus any pixels connected four directionally to the starting pixel of the same as the starting pixel plus any pixels connected four directionally to those pixels, also with the same color, and so on. Replace the color of all the aforementioned pixels with color. Return the modified image after performing the flood fill. So the example they give you, right, they've got 111, 110, 101, and they're going to fill from the middle tile with a 2, and that's going to expand to affect almost all of the ones except for the one at the bottom right because it's not connected four directionally from any of the connected tiles. And the zeros that exist here are not affected either. If we look at the constraints, the m is going to be the image length, n is going to be the image I of length, and the m and the n are going to be between 1 and 50. The image ij and the color are going to be between 0 and some giant number, and SR is going to be between 0 and M, and SC is going to be between 0 and N for the rows and columns. All right, let's take a look at how we can solve this problem. So to start with the flood fill problem, let's look at the input they gave us and the expected output. So you can see we have 111, 110, 101, and the expected output is going to be 222, 220, 201. And there's a few things that we can sort of learn from this or glean from this. But there are some things actually that maybe are not as obvious as you might think. So yes, if something is not connected four directionally adjacent to the starting tile, which in this case was the center tile here, it won't actually spread to those tiles, so which is why the zeros and the ones are unaffected. However, there's another case that they're not quite showcasing here in the example, which is if, for example, they were to try to fill the center one here in the input with a 1, that actually would result in the same input as the same output as the input. Basically, if we try to fill with a color that is the same as the starting color, that's basically a no-op. We don't want to do anything in that case. But in all the other cases, we should be able to expand from the starting pixel. So the first insight I want to share is you need to keep track of the initial color. And when I say the initial color, I mean the color that we are going to start the flood fill from, not to be confused with the color they pass you in the function. So let's look at the example and see how we might think about doing this recursively. So let's look at the example they gave us. We're going to start off by filling row 1, column 1 with color 2, which is going to be that center tile. And as we look at the difference between the initial color, which is 1, and our fill color, which is a 2 here, we know that we're going to be able to fill the center tile with the 2. Now let's look at the logic that we need to follow whenever we're going to expand our fill to the adjacent connected tiles. If the tile that we're expanding to has the same initial color that we started at, which is the 1, then yes, we can fill this, right? We can fill this, we can fill this. We cannot fill this, and we cannot fill this. So the result is going to be this. The red ones indicate that basically we did a comparison, but we weren't able to spread the fill. These other twos we're going to be able to expand from in the next step. So if we look at this 2 here, can we expand up here out of bounds? Well, of course not. We cannot expand out of bounds. Can we expand to the left? Yes, we can, because it's not the same color, or rather it is the same color as the initial color that we started on, the 1. And we can also do the same to the right, but can we expand down below? And that's an interesting case that you need to handle, otherwise you're going to have infinite recursion. You do need to say, actually, if the existing color is the same as the fill color, we can't proceed anymore. But actually, if you just make a comparison to check if it's the initial color, that'll handle that case for you. And so if you perform that spread operation from the connected tiles here, right, from the 2s that we expanded to, you're going to get the eventual output, which is the following. And here is your final output solution. So the time complexity of this is going to be m times n, where m is the rows and n is the columns. And the space complexity is also going to be m times n, because we're going to eventually need to copy the grid, and also our recursive stack in the worst case could technically go through the whole grid. All right, let's take a look at the code now. So the first thing that I want to do is make a copy of the image because the parameters in Swift are immutable, and I also want to keep track of how many rows and columns there are. The next thing that I'll kind of want to do is track the initial color, right? So the initial color is going to be equal to the image at srsc. And what I need to do now is check if the color is the same as the initial color. Go ahead and return. You can write this as a guard. I'll keep it as an if for now. And actually, we don't even need to perform any of the variable declarations or copying of the image if the initial color is actually the same as the fill color. All right, so we know we're going to have probably some kind of recursive function called explore, I'll call it, for example, and we're going to eventually call this explore with the initial coordinates, the SR and the SC for row and column, and at the end of this, we're going to return our image. Okay, so in the explore function, we know that we need, let's say, a row and a column. And we need to do a bounds check to see if we're actually in bounds here. Well, it's true that we're going to start in bounds, of course. We don't know that this recursive explore function is guaranteed to do that, and it's typically better to set up your base cases in your recursive functions rather than look before you leap. Now we need to check if the initial color is the same as the color at the current row. And what does that tell us? Well, if the initial color is equal to the same color as the image row, that tells us we can actually expand the fill. So what we might do instead, and I could write this as a guard, of course, we can say if our initial color is not the same as this color, go ahead and return. Otherwise, we can actually fill the color here. So we can say image of row column is equal to the color, which is the parameter all the way at the top, which is basically the fill color. And then this will also handle the case where we do not recursively update back and forth, right? So if we fill something with a particular color and we eventually explore back to the same tile, this if condition will block that from proceeding. So now we need to explore the additional positions that are connected. So I'll say positions is equal to an array. The way I typically do this, right, is I'll say row, call, and then I'll paste this a few times. And then what I do is I typically go top, right, down, left like a clock. So to go top, we're going to say row -1. To go to the right, column +1. To go down, we'll say row +1. And to go to the left, we're going to say column -1. And because I use them or declare them as tuples, I can go for new row, new call in positions. And here we can perform our explore function, right? So we'll say explore, we'll say new row, new call. And because we have bounds checking up here, we don't need to worry about that. So this should be pretty close. Probably just run it to see if I made any mistakes here. Return, oh wait, so I actually do need to return an image up here. Pass the base case. Now we'll submit it to see if it passes all the cases. And there we go. I hope you enjoyed this video, and I'll see you in the next one.